I'm Anil Kumar sharing with you some key concepts on curve sketching. First thing which I want to emphasize here is that we should not follow the algorithm blindly. Now that is very important. Algorithm which is being taught to you for curve sketching has at least 10 points, right? So if you start discussing all the 10 points to sketch graph, in that case you will run out of time. So time is critical. Remember, take this as your test, right? We have very simple three functions. These are the simplest you can get in any test. We have a polynomial and two rational functions. And let us say the time for you is 20 minutes. So what I would like you to do is sketch graph of these three functions, follow the algorithm and see where do you reach. Are you able to complete your work or not? That is very important exercise to do. Now here is a neat strategy to work with. The most important criteria to sketch any curve is to analyze type of function. Now this is not part of your algorithm, type of function which I'm talking about. So based on type of function, we have to choose which of these 10 points should you work on. Do you understand? If you do that test before getting on with the algorithm as a whole, you are going to save a lot of time. For example, when we are talking about a polynomial, what is important here? Well, you can see the degree, right? You can see the leading coefficient, and then you know end behavior. So once you know that, you exactly know what to work on. Now this is degree 4, leading coefficient positive, right side up, both facing up. That means you're also looking for absolute minimum, right? And of course, x and y intercepts. So these are good enough points to sketch fairly accurate polynomial. Do you agree with me? So that is what you have to concentrate on while working with the first function, right? Now if I look at this, then since the degree of numerator is higher than that of the denominator, so the points here to look into is oblique asymptote. And this gives you vertical asymptote, right? Now those are critical and they actually provide you with the structure of your curve, right? So this gives you a structure. And now you can refine by finding maximums and the minimums. Do you understand? So that gives you kind of a strategy, and if you work with a strategy, you can efficiently sketch very accurate graphs. That is the idea. So I hope you understand, right, what I'm trying to say. Now in the third case, again, we are looking for horizontal asymptote, vertical asymptote, right? That's it. Is that okay? Just take intercepts and you're good to sketch this particular function. You really don't have to bother much. You can have few test points if you want. You know the behavior of 1 over x. It is kind of a graph which is kind of like this, right? So there's not much to think about. But if you think like this, then you can select how to use algorithm intelligently, right? Now let me give you some difficult questions to work with, which I'll like to give like this. Let us say one of my functions will be, let us say, a radical function as we say x plus 2 to the power of, let's keep it simple, let's say 2 over 3. So that is a radical function, right? Or I could give you another function writing that as, let me write here, let's say p of x equals to, let me say x minus 2 this time, and let me flip this, 3 over 2. So as soon as you see the radical powers, what is important here to understand is that we are looking for a cusp or a corner. Do you see that? Cusp or a corner, which becomes very critical. Now, if the radical is 3 over 2, you're also looking for restricted domain. Is it okay? Domain should be greater than or equal to 2, right? Now with that in mind, you can actually sketch both these graphs very easily. So let me just sketch it. So we're just making a rough sketch here, right? The whole idea is to understand the concept. So this graph here, 0 at minus 2 and 2 over 3 over the cusp there will be kind of like this. How about the other graph here? Now this is cubic, right? So it goes up. It will be kind of like this. Do you see that? So the equation itself tells you what type of graph you should be sketching. So I actually wanted to emphasize on these points rather than sketching the functions themselves. But now, when we have talked about a strategy, let's take few more minutes to sketch all these functions one by one. Does make sense to you, right? So let's begin with the very first function, which is polynomial. So it is f of x equals to x to the power of 4 plus 4x cubed. So you can find first thing is what is f of 0. F of 0 is 0. Perfect. Then we look for x-intercepts. So let's factor this. So we can say x cubed and we have x plus 4 here. So that gives you 2 zeros. So we have a 0 at x equals to 0 and the order is 3, right? And then we have x equals to minus 4, the order is 1. It is kind of important to mention order here, or multiplicity, which we say, right? Multiplicity. That really tells you the nature of graph at the x-intercept. Perfect. Now, we are also expecting, so let me use this space to sketch this graph finally, right? So what we saw here was degree is 4, right? So that means both same side, and this is positive, this is positive. So that means right side up and both facing up. Perfect. Now we have got few zeros here, 0 at 0, and then we have a 0 at minus 4. Let's say this is minus 4 for us. If you're coming from this side, at minus 4 is linear, and at this point it is cubic. So that practically gives you the whole graph. What is left here is to find the local minimum, right? So for local minimum, let's find the derivative. So f dash x is equal to, we'll differentiate this. We have 4x cubed plus 12x squared. And if you factor this, let's do it here itself. So 4x squared is common. We get x plus 3. So we get 2 zeros here. So for the derivative, we get 2 zeros, which are at 0 and minus 3. So let's analyze these zeros. So these zeros for us are at 0 and at minus 3. So if I take a value which is, we know fx squared is always positive, right? So we know this part is always positive. This is always positive. So basically we are looking for that sign if I have number which is more negative than minus 3, I get negative. But if it is on the right side of minus 3, I get positive. Now that clearly indicates that the function should be going down, up and up. So that gives you a local minimum at minus 3. Does it make sense? So that gives you local minimum at minus 3. So you can find the value of the function at minus 3. So if I substitute minus 3 here, I get the value for local minimum, right? So let's do it. So within brackets, we have minus 3 to the power of 4 plus 4 times minus 3 cubed. And that gives you minus 27. So we have minus 27 here. That means I could actually sketch this graph kind of like this. So we have something like this coming down here, going up, following this curve, and then like this, where the turning point is at minus 27 and this point is at minus 3. That 0 is at minus 4. This is at 0. This actually gives me perfect graph for the time being. Do you see that? With this, you exactly know the graph, but depending on your other criteria of the test paper, you could go for second derivative, but not essential. Do you see that? So first derivative is 4x cubed plus 12x squared. Second will be 12x squared plus 24x, which could be written as, if I take 12x common, I could write this as x plus 2. Now that means we can analyze for two values here, which are x equals to 0 and minus 2, right? When it is 0. So analyzing the second derivative for these points, we can take test point as minus 3, minus 1 and plus 1, correct? So if I write this function, which is 12x times x plus 2. So if I substitute negative, both are negative, right? Both are negative. And so we get a positive value here, right? Now if I substitute negative 1, then only this is negative, not that. So we get a negative value. And for plus 1, we get both positive, correct? So that means the concavity here is concave up, concave down and concave up. So as expected, we have point of inflection at x equals to 0 and the concavity intervals are as shown in the graph. So what we did was we confirmed our graph, right? But no added information. Do you see that? No added information. The information which you got by analyzing the second derivative was already there when you had sketched the graph. So at times, if you have to cut upon the time, you could do this part. You could do away with this part. Does make sense to you, right? Now, let us try to sketch the graph of the function g of x equals to x squared minus x plus 2 divided by x minus 2. If you analyze, you know it is a rational function. Degree of numerator is higher than denominator. So what we expect is an oblique asymptote, right? And we do have a vertical asymptote at x equals to 2. So we can begin with easy things first. That is vertical asymptote at x equals to 2. And to find the oblique asymptote, we need to divide, correct? So let us divide x squared minus, let's do it here. So now we will divide the function, which is numerator is x squared minus x plus 2 by x minus 2, right? So x times we get x squared minus 2x, and then you get x plus 2 plus 1 will give us x minus 2, a remainder of plus 4. Do you see that plus 4 here? Now, that also gives you that we have oblique asymptote at y equals to x plus 1. That is the oblique asymptote. Now, since this remainder is plus 4, it tells you that on the right side, if this is my oblique asymptote, in that case, when we are moving, when x is approaching from right side, you are approaching from the top, that plus 4. Do you agree with me? However, if x is very large negative value, right? So if x is very large negative value, basically what I'm trying to say here is once you divide, you could write this as x plus 1 plus 4 over x minus 2. Do you see that? So that is how after this division you should look at your function and now analyze. So if I write a negative large value for the given function, right? In that case, this is negative, right? This is negative. That means the value is lower than x plus 1. So for the negative portion, you are approaching from this side. So that gives you behavior near the asymptote. Is that clear? So this we are talking about behavior near oblique asymptote. Is it okay? So OA is oblique asymptote, right? Which I am writing as OA. Is it okay? So oblique asymptote, which is y equals to x plus 1 in our case. So I hope this part is absolutely clear. Once you divide, write it like this so that you understand that when x is approaching positive infinity, right, then g of x is approaching from above. And when x is approaching negative infinity, g of x is approaching from below. Oblique asymptote. Is it okay? Above oblique asymptote. That is what we're trying to say here. Now this is extremely important criteria. Okay, and that gives you actually more or less your graph. Now, when you have a function like this, another important thing to consider is maximum and minimum. So this graph will always have local maximum and minimum. So for that, we need to find the derivative, analyze the derivative, and get the result. So we'll sketch here. Let's find the derivative now. So g dash x is the first derivative, denominator square, which is x minus 2 whole square. Derivative of numerator, which is 2x minus 1 times denominator x minus 2 minus. Derivative of denominator is 1, so we get x square minus x plus 2 here. Now let's simplify this. So when you open this up, you get 2x square minus 4x minus x plus 2. That is minus x square minus becomes plus x minus 2 over x minus 2 whole square. And this gives you 2x square minus x square becomes 3x square. X square, I'm sorry. So it becomes x square. Minus 4x minus x plus x is minus 4x. Plus 2 minus 2 is 0. So we get this as x minus 2 whole square. Now that could be factored. You could write this as x minus 4 over x minus 2 whole square. Now let's try to analyze the first derivative. This is one of the most critical part of our curve sketching in this particular function, right? So if you analyze what you have here is, let's say, we have two zeros and a vertical asymptote. So x equals to 0, 4, and 2. So we're looking at these points, x equals to 0, x equals to 2, and x equals to 4. We're trying to analyze the second derivative. First derivative, g of x, g dash x. Okay, so let's take test points. Test points on this side will be -1. Here we could take as 1 and 3 and let's say 5. Okay, so at these test points, these are our factors. So let me just sketch boundaries for the interval. Okay, since I'm running out of space here, I like to conserve this space a bit. We can't do much. So the factors here are x minus 4, and denominator is always positive, so let's not bother about it, since we know this denominator is always positive, is okay, square term, so let's not bother about it. So we'll do these two factors, the numerator part. So with negative, it is negative, these two are positive, this is -4, so negative, I'm sorry, I should have written x and x minus 4 here, okay, and this is positive and this is also positive. At 3 it is negative. So the net result here is that two negatives will give us positive, this will give us negative, negative, and here we again get positive. Correct? Clearly shows that at 0 the graph is going up, positive slope, right? And this is negative slope, this is also negative slope, and then positive slope. So clearly we do have a maximum at x equals to 0, right? That is a maximum. And we have a minimum at x equals to 4. So at x equals to 4 we have a minimum, and at x equals to 0 we have a maximum. Correct? So now let us find these values. So at 0, g of 0 is equals to, if I substitute 0 here, I get 2 over -2, which is -1. And if I substitute 4, then g of 4 will be equals to 4 square minus 4 plus 2 over 4 minus 2, correct? Let's take the calculator, calculate this value. So we have 4 square minus 4 plus 2 equals to, divided by 4 minus 2, which is 2. So we get a value equals to 7. So that gives us the local minimum, right? So local maximum, minimum we have got. Now we are in a good position to sketch our graph. So let us sketch it. So what we have here is, let's put all these things which we have got right there in the form of a graph. So let me draw the asymptotes first. So we have asymptote at x equals to 2. Let us say this is x equals to 2. So this is the asymptote at x equals to 2. And then we have an oblique asymptote at which is x plus 1. So that is the oblique asymptote. And let's say this is the oblique asymptote for us. Right, so that becomes the oblique asymptote. And as far as the graph is concerned, we have a local maximum at 0. So we have a maximum at 0, value is -1. So let's say this is your local maximum. We also know that the graph approaches from above, right, this side, and from below this asymptote, correct? Keeping that in view and maximum here, we could sketch this graph kind of like this. Do you see that part? And on this side, we know this is a vertical asymptote. It goes like this. Does it make sense to you, right? Now, I kind of not maintained the scale since we know this point is actually at 4. I mean, I've shown it closer since I would have run out of my space here. So this point is actually, let me write down the point clearly. It is at 4 and the y value for this point is 7. So it is here 7. Do you see that? But I hope it's clear. And this point here is at -1. Perfect. So that becomes the graph of this particular rational function with oblique asymptote y equals to x plus 1. So this point is -1, that is +1. Does it make sense to you, right? So what we really need to do here is only analyze the first derivative. So a word of caution, let me write here. Do not, let's say do not go for second derivative. Very important, right? Otherwise you'll waste a lot of time. Second derivative is not easy also to analyze and you'll run out of time. So that's kind of critical to understand. So with that, let's move on to the next. I hope you learned a lot. Have a good look at the graph. Okay. Now we are at the end of the video. We'll sketch the function h of x equals to 3x minus 1 over x plus 1. So as far as the structure is concerned, it is kind of a reciprocal function, right? It's kind of reciprocal function, mod if transformed. So what is important for us to find is vertical asymptote, which is at when the denominator is 0. So which is when x plus 1 equals to 0, it is at x equals to minus 1. Okay? And then we have to find the horizontal asymptote, which is when x approaches positive infinity or when x approaches negative infinity. Very large values, in that case what happens to h of x? So we say h of x approaches when the degrees are same, right? It is ratio of the leading coefficients, it is 3. So our horizontal asymptote is y equals to 3, right? So important thing here is to remember for horizontal asymptote, when same degrees for numerator and denominator, it is the ratio of these. Is it okay? Fine. So that is how you get your horizontal asymptote. So we found horizontal and vertical asymptotes. Another critical point is to find the intercepts for this particular graph. So you can find the y-intercept, which is basically the value of function when x is 0. So if I substitute x equals to 0, I get 0 minus 1 over 0 plus 1, which is negative 1. And then let us now find the x-intercept. So x-intercept means h is 0. We have to solve this equation. Is that okay? I mean minus 1 over x plus 1. So solving this, we get 3x minus 1 equals to 0, which gives you x equals to 1 over 3. So we get all the required information to sketch this function from these values. So I hope that part is very clear, right? That actually defines our function totally. So with this information, let us try to sketch the graph here. So 1, vertical asymptote at x equals to minus 1. So let us say this is our vertical asymptote at x equals to minus 1. Right, so this is x equals to minus 1, vertical asymptote. Now, let us sketch the horizontal asymptote y equals to 3. So y equals to 3, let us say this is y equals to 3, horizontal asymptote. Perfect. Now, let's find out where the x and y intercepts are. So the y-intercept is at minus 1 and the x-intercept is at 1 over 3, somewhere very close here. Correct? So these 2 points indicate that we are on this side of 0, right? So we could sketch this graph kind of like this. Does it make sense? And on this side, you could take some test point and sketch the graph like this. Correct? Now we know what these points are. For accuracy, what you can do is, you have to write here, this is minus 1, this is 3, or you write y equals to 3 here. These are good points to mention. So what you can do is, you can find what is the value of function at, let us say, this is minus 1 here, let's say at minus 2. Right? Once you find this value, you can plot this somewhere here. Is that okay? Similarly, you can find what is the value of the function at 2, right? Or even 1, right? Or even 1. So when you write these values, you get your points And these 5 points will give you accuracy. You understand? So calculate these points if you really want to sketch perfect graph. I'm not doing it here, but it's easy. Just plug in the value, calculate your answer, plug it in, and sketch. If you have time, if you have extra time. Else, the graph which we sketched is actually perfectly fine. Right? So write your functions, this origin, that's it. So I hope you have learned what you should be doing in curve sketching. I should say what minimum you should be doing in curve sketching to get maximum marks. If you have extra time, then you can always add information. So I'll say add information if you have luxury of extra time. That is very important. Otherwise, first sketch the basic for all the 3 functions. Then you can always go back and add those informations. So I hope this point is clear. Feel free to write your comments and share your views. I've already discussed a lot about this. Look into the links which I have provided for other functions and understand curve sketching and try to get good marks also. Hope that works for you. If you share and like my videos, it'll be good for me. Thanks for watching and all the best.